Alright, I think I'm gonna get started. It's currently 7:04, so I think that's fine. Alright, welcome everybody. Tonight we're going to be talking about classic cryptography. And yeah, let's just get started. So first things first, just a brief history lesson. So what I mean when I say classic crypto is any sort of cryptographic system that was used before World War II. Up until that point, most of the crypto systems used by the world fit into some of the categories that we will be discussing today. But after World War II, after the Enigma machine was cracked by Alan Turing, the world collectively said, well, okay, so we're not going to use this style of cryptography anymore. Let's try and think up something better. And that gave rise to modern crypto systems like RSA and ECC and so on. But we're not going to be covering those today. We're going to be covering the older stuff. The reason you don't see this type of stuff anymore is because it's really easy to break, mostly. Nobody uses it to actually protect their vital information. So what's the point in learning it? Well, classic crypto there's not much in the way of, like, it's pretty obscure, so not a lot of people know too much about it, so it can show up as sort of like a gotcha challenge in some CTFs. And also, it gets you in the right mindset for approaching the more modern stuff that we'll be covering in a week or two. And also, it's just kind of fun to do. It's a little bit silly, it's pretty simple. So, yeah. So first things first, I just want to get some basic terminology out of the way. So say we have Alice who wants to send a message to Bob, and she doesn't want any spies to intercept her message and read it. So the message that she's going to be sending to Bob is called the plaintext. And she's going to encrypt that plaintext using a cipher, which is just a method for scrambling or changing the message so that it's unreadable to the naked eye. And that cipher will take as an input the plaintext and a key, and it will produce an encrypted message known as the ciphertext. And the key is usually some sort of number or a string or any other information format that you can use to encrypt. So today we'll be covering two types of ciphers. The first is the substitution cipher, and the second is the transposition cipher. So substitution ciphers, as the name implies, take a plaintext, like an English plaintext made up of ASCII characters, scans through each letter, and swaps it out for a different one. So in a sense, you could think of substitution ciphers as replacing the alphabet that was used to generate the plaintext, and we'll get into a bit more detail about how that actually works. Transposition ciphers, on the other hand, don't change the alphabet. They don't replace the letters in the plaintext. They just move them around a bit. So they'll say swap letters based on location, or somehow transpose the plaintext so that it looks a bit weird. And we'll cover some of those as well. Transposition ciphers you don't see as often, but they do make for some fun programming challenges. Alright, so first up is the substitution cipher. And like I said, substitution ciphers work by scanning through the plaintext, looking at each letter, and replacing it based on some sort of scheme. So this replacement scheme might follow a pattern, or it might be random, and if it does follow a pattern, there's two ways that it can go about replacing each letter. So the first kind of subcategory of substitution ciphers are the monoalphabetic ciphers. That's kind of a loaded word, but all that really means is that you take the alphabet that was used with your plaintext and replace it with a new alphabet. So that means that every letter in the plaintext, as it's scanned by the cipher, will be replaced by the same letter in the ciphertext. So for example, if you have a string that has a bunch of H's in it, and you encrypt that with a monoalphabetic cipher, every position at which there's an H in the plaintext, there will be a Y at that same position in the ciphertext. So the letter H is always transformed to the letter Y, for example. Polyalphabetic ciphers, on the other hand, are a bit different in that besides just taking into account what the letter is when transforming it, they take into account the position of the letter in the string, or some other factor that will not always change the same letter in the plaintext to the same letter in the ciphertext. So if you encrypt a string with a bunch of H's in it with a polyalphabetic cipher, then the ciphertext will not have Y's in those same positions for every occurrence of the letter H in the plaintext. So before we go into actual examples of substitution ciphers, I just want to kind of lay the groundwork for how we express the operations on the ciphertext. So we want to be able to perform arithmetic on letters themselves, which kind of might seem weird in isolation, like the concept of math does not really apply to English letters, but what we do is we just assign numbers to each letter. So for example, A is assigned the number 0, B is assigned the number 1, up through Z, which is assigned the letter 25, the number 25, and at this point we can treat the letters as if they were the numbers that they correspond to. So we can perform basic arithmetic like addition and subtraction. So we could say add the letters Y and E, which have corresponding values 24 and 4. And the result we get from that is 28. Now 28, as shown by the table, does not map to any single letter. So what we do is we mod the result by 26 so that we get back into the range 0 to 25. So in this case, Y plus E results in 2, which maps to the letter C. Alright, so let's get into the meat of the thing. The first type of substitution cipher I want to cover is the Caesar cipher. Now, as the name implies, this cipher was used by Julius Caesar over 2,000 years ago in times of war. So he would encode a message, or one of his generals would encode a message with this scheme and give it to his messenger, and the guy would run off to go deliver it. And if the messenger was ever captured, then the enemy wouldn't be able to tell what the message he was carrying actually was. So the Caesar cipher is a monoalphabetic cipher, and that means that you just replace the alphabet of the plaintext with something else, and in this case you replace it with a single letter. So, or you actually shift the alphabet by a specific value. That's what I meant to say. So what you do when you're performing a Caesar cipher is you select a single letter as your key, and then you shift every letter in the plaintext by that amount. So for example, if we choose the letter H as our key, H corresponds to the number 7. So if we want to encrypt the plaintext hello world, all we do is we add 7 to every letter in the plaintext, and then if it goes over 26, then we just mod by 26. So in this case, we have the string hello world, we apply H as a key to it, and we get out this ciphertext. Now if you want to decrypt a Caesar cipher, you do the same thing in reverse. So that would mean subtracting 7 from the ciphertext. So if we subtracted all H's from the ciphertext, we would get the plaintext hello world. So another variation of the Caesar cipher is ROT13. In this case, ROT just stands for rotate, which means like it refers to the kind of rotation of the alphabet as you shift it over and over again. And 13 in this case is just the value of the key. So in general, the Caesar cipher is very easy to break because the key space is only 26 large. There's only 26 possible keys. For like, if you tried to encrypt a plaintext with the key 27, the result you get is actually the same as if you had tried to encrypt it with the key 1. So the only meaningful keys that you can use are the values 0 through 25. So I actually have an example of how easy it is to brute force the Caesar cipher. So we have this string here, the URYYB. So I've written up a short script called Caesar brute force.py. All it does is, so I implemented the Caesar cipher in Python. All it does is it takes a command line argument and prints out every possible shift of that input using the Caesar cipher. So, for example, if we call it with the string, that first string in that list there, it'll print out every possible shift of that string. And you'll see that when we use a key of 13, that results in the string hello world just falling out of the program. So as you can see, it's very fast and very easy to actually brute force a Caesar cipher. All you do is just run through every possible key and look for English words. And I will leave these other two examples as an exercise to the reader. So this site here, Romkin.com, is actually, as an aside, it's a great site for a lot of classic crypto tools. We open it up here. So it has a bunch of different possible ciphers that you can run through. Some of them aren't even ciphers, it's like base 64. But most of the ciphers that we will be talking about today can be found on this site here. So that's just a good resource if you're looking for more. Oops, sorry. Let me fix this. Alright. So next on the list is a cryptogram. So cryptograms are pretty similar to a Caesar cipher. They're monoalphabetic, but in this case the way that the key that you generate is actually random. So you generate a random alphabet and replace the alphabet used for the plaintext with that random alphabet. So for example, it's kind of like a mapping of one letter onto another. So as an example, say we have the string hello world. We can apply a cryptogram to it that maps H to Q, E to F, L to Z, and so on, and generate a ciphertext that is generally unreadable. Now, attacking this scheme doesn't really seem intuitive at first. There's not really a clear way to attack this, because if you just have the ciphertext, there's really it doesn't seem to be a way to recover the key from it. Well, turns out that the English language itself will be able to help us in this case. So what we can do is take advantage of the fact that the English language doesn't distribute all its letters the same way. So for example, everyone knows that the letter E is the most common letter in the English language. Like, it appears in more words than any other letter. So if we have like a really long ciphertext and see that G is the most common letter in the ciphertext, then maybe we could surmise that G was mapped from E in the plaintext. So E in the plaintext was transformed into a G in the ciphertext. And this relies on the fact that you have a long ciphertext, because if you have a really short ciphertext, then you won't be able to really calculate any sort of meaningful frequency analysis on it, because I guess because of the basic properties of statistics. So the longer your ciphertext is, the more feasible a frequency analysis attack is on that ciphertext. You can also, besides just looking at single letter frequencies, you can look at the frequencies of two-letter combinations. So here we have the 24 most common two-letter combinations in the English language. Now there's like 320 total possible combinations of two letters, but this can help you if you need just a little bit more information out of the ciphertext. You can also do trigram frequency analysis, where you look at combinations of three letters, but this is less useful because it requires an even longer ciphertext than normal to actually correctly calculate frequency analysis that would be useful to you. So now let's move on to polyalphabetic substitution ciphers. So we saw that the Caesar cipher and the cryptogram are generally pretty easy to brute force, and that's because they substitute a single alphabet in. The Caesar cipher specifically uses a single letter as a key. So what we want to try instead is, instead of a single letter, we want to choose a string as our key. And in fact, if you think about it, this Caesar cipher is kind of like a subset of this cipher here, which is known as the Visionnaire cipher, invented by some French guy, I'm assuming. So the way Visionnaire works is you choose a key, which is a string, and you have your message. So for example, here is my very private message. That's our plain text. What you do is you tile the key so that it equals in length to the plain text, and then you just add the two strings together using the same type of arithmetic that I talked about earlier. So if you do that, you get this ciphertext here, and this ends up being a lot harder to break than the Caesar cipher, although it is breakable. So the first step in breaking Visionnaire is to find the key length, because if you don't know the key length, you're basically stuck guessing at what could possibly be a very, very large key space. So the first thing we want to do is find the key length and narrow down our search space. So the way we do that is by looking for patterns or repeated sections in the ciphertext. So in this case, we see both the plaintext, the key, and the ciphertext, but you could just apply this to the ciphertext. This is just for illustrative purposes. So in this case, we have the plaintext. Crypto is short for cryptography, and the key that we use to encrypt it is ABCD. Now if you notice, we have a repeated phrase in the plaintext, and that repeated phrase just so happens to align with a repeat in the key. So when we encrypt the plaintext with the key, we will end up with a repeated phrase in the ciphertext, highlighted in red. And if we look at the distance between these two repeated segments, we see that they're 16 apart. Now this tells us something about the key length. It tells us that the key length divides 16 evenly, because we now know that there is a repeated section in the plaintext, most likely, that lines up with a repeated section in the key. Now the length of that repeat might be 16, or it might be 8, and we just got through 2 repeats. We went through 2 cycles of the key. Or it might be 4 or 2 or 1, or any divisor of 16. Now how do we narrow it down from here? What we do is we try and find other repeated sections, look at the distance between those repeated sections, and look at the common factors between all the distances that we find. So if we find a repeated section that's only 4 apart, then we know that it the key length must either be 4, 2, or 1 at that point. So you can repeat this a bunch of times to find the key length. So now that we know the key length, breaking Visionnaire essentially boils down to a bunch of Caesar ciphers that we can solve with frequency analysis. So to illustrate that, I'm going to highlight the plaintext and key where the characters in the key are the same. So what I mean is this C is encrypted with the same value as this T and this S and this T and so on and so on. And this R and O share the same key. So what we can do then is kind of separate out all the same colored letters into 4 separate Caesar ciphers. So we know that this ciphertext here was encrypted with the same key for each of its letters. Same with this one, same with this one, same with this one. And if these sections are long enough, then we can actually perform a frequency analysis attack on them to recover the key. So once we recover the key, which is ABCD in this case, then we're done. At this point, any future communications that we see with this key can be very easily decrypted. So another polyalphabetic cipher that tries to actually solve the problem we just saw. So with Visionnaire, the problem is that if our key repeats and it coincidentally winds up with a repeat in the plaintext, then we can gain some information about the length of the key. The one-time pad scheme tries to fix this by saying, hey, you know what? Let's just set the length of the key equal to the length of the plaintext, and let's make the key completely random. That way it can't be predicted. So the math involved is basically the same as with Visionnaire. You take the value of the letter in the key and add it to the value of the letter in the plaintext to get the value of the letter in the ciphertext. So relatively straightforward, except the key here is the same length as the plaintext and it's completely random and it can't be predicted. So this essentially, if you do it right, makes one-time pad 100% impossible to break. Because if we have, so if I go back, we have this hello world encrypted with this random key and we have this ciphertext. If we have this ciphertext and we don't know the key or the plaintext, we basically have no information about the plaintext because we can choose any plaintext and generate a key that decrypts the ciphertext to that plaintext, and there's no, it's not unique. We can have any plaintext and have the ciphertext decrypt to it by just changing the key. So we have no information about the key itself. However, that's assuming that you use one-time pad correctly. If you it's called one-time pad for a reason, because if you ever reuse a key to encrypt 2 plaintexts at the same time, an attacker can gain quite a bit of information about both plaintexts, even so far as to figure out what those plaintexts actually are. So let's consider that case. If we have 2 plaintexts, P1 and P2, and we use the same key, K, to encrypt them, then we will have 2 ciphertexts, P1 plus K and P2 plus K. So if an attacker has these 2 values, then they can simply take the difference of C1 and C2, the 2 ciphertexts, and the K's in this case will cancel out and we'll end up with the difference of P1 and P2. Now, this result won't actually look like any sort of English sentence. It'll still look like kind of just a garbled mess. But if we know that P1 and P2 are in English, then we can start guessing words in one plaintext to try and see if it reveals words in the other. Now, this is still pretty hard to do in terms of computation, but it makes it a lot easier. I mean, it takes you from 100% security to less than 100% security, which in cryptography is not what we want. We always want to be 100% secure. So this process is known as cribbing, and is the reason why if you ever use one-time pad, obey the name. Use a key once and throw it away. So that's all I have for substitution ciphers. So now let's move on to transposition ciphers. Like I said at the beginning of the talk, transposition ciphers don't change the alphabet that's used with the plaintext. Instead, they just rearrange the plaintext to create the ciphertext. And in this case, frequency analysis doesn't help at all, because the ciphertext is made up of the exact same letters as the plaintext was. So the frequencies of all the letters will be the exact same between the two. And you don't see these as much as substitution ciphers because they're more for fun. They're more kind of, just play ciphers and so on. So an example of one is the rail fence cipher, where you take a plaintext and arrange it in a zigzag pattern up and down. And then to read the ciphertext off, you take each line and just append all the characters. So we have hello world, we write it out in a zigzag, and then just read off each line one by one and append them all together, and that's our ciphertext. And rail fence takes as a key the height of the rails and an offset. So for example, if we had a rail height of 6 and an offset of 1, we could say that we have 6 lines here, and we put the first letter on the first kind of, or I guess the second line here, and go up and down, and then read off line by line, L, H, R, D, so on and so on. So this is a fun programming challenge. So I challenge you to actually try and brute force it by just trying a few parameters. A hint is that the offset in this case is 0. So here's the ciphertext. Try and figure out what the plaintext is. And I actually forgot to delete the slide, so don't pause there if you don't want to see the spoiler, which is the plaintext. Alright, so the last cipher that we'll cover today is columnar transposition, which was also used a long time ago in times of war. Basically what you do is you create a square that has as many subsquares as the number of the number of letters in your plaintext, and you write out the plaintext row by row in your square, and then as a key you choose an order of columns. So 3142 means this column first, this column second, this column third, and this column fourth. And then to generate the ciphertext, you read off each column in order. So TKA and then ATN, and append them together, ACD, TAW. And that's your ciphertext. And if you know the ciphertext and the key, then you can create the same square and start writing letter by letter vertically in each column, like this, and then read it out row by row to get your plaintext. So that about concludes it for today. If you have any questions or want to learn more, just ask in the Slack. I'm sure anybody would be able to help there. And if you want some practice challenges, I have some links here. So I know we've mentioned Over the Wire in the past because they have their Bandit series, I think it was called, which helps you learn the Linux shell. They have also a classic crypto kind of course that you can try out, and also CryptoPals. CryptoPals is pretty great. They have a bunch of kind of problem sets, which is just a bunch of different problems in different categories, and it goes all the way from classic crypto up to the super modern attacks that have only been around for like 10 or 15 years. the ones where you have to know quite a bit of math to understand them. So they cover a wide range of knowledge, so definitely check them out if you're interested. So in that case, that pretty much wraps it up. So on Friday, we will be covering block ciphers, which are pretty new comparatively to the 2,000-year-old Caesar cipher. So if you're interested in more crypto, come see that talk.